Are we on? Sweet. Hey, everybody. Welcome to the Audio Programmer Meetup. And we're all the way over here in Dublin today. I'm so excited to be here. I wanted to thank Maynooth University and Sil and Ryan and the rest of the audio developers over here in Ireland for inviting us to come up and have our live stream here this month. And this is a more intimate audio programmer meetup than you may be used to with seeing in-person meetups such as ADC or the things that we've done in London. And I really enjoy that because it's an opportunity for us to get back to the grassroots with the community, just going around the world, talking about audio programming and doing what we love. So we have 5 great talks for you this evening. I'm not going to keep you held up with a lot of platitudes. I'm going to go ahead and jump into the first talk, who is from one of the people that invited us to come up here, Sil Morrison. So Sil is an audio software engineer with Kalide Systems and develops his own plugins under SLM Audio. And he is giving a talk called Freaky Diffuse Noises, Getting Creative with FDNs. Take it away, Sil.
Let me mess around with Keynote for a second. We go like this, and then we go like this. And I move my speaker notes over here. Right, I'm Sil. This is Mad. Thanks everyone for coming. So yeah, I thought I'd start us off with a few existential questions. Reverb. What is reverb? Am I a reverb? Can I somehow become a reverb? Who is the most famous reverb? What are the top 5 reverb techniques that doctors don't want you to know about? Are there any hot reverbs in my area? What should I do with a reverb when I'm finished with it? Is reverb biodegradable? How can I grow my reverb to at least 13 inches fast? All of that and more in freaky diffuse nonsense. It used to be called noises, but getting creative with FDNs. So the reason I want to talk about this is reverb, I think, for a beginner, is one of the most gate-kept effects, for better or for worse. Most published algorithms and papers don't lack technical details, but they do lack coefficients and a general kind of why someone would choose these values and that kind of thing. Which makes sense, you know, a reverb designer might take months tuning some of these numbers and not want people just to be able to just go like, oh, well, this is my reverb now. The problem is for someone wanting to get into it and mess around with it without a heavy theoretical maths background, it's pretty difficult. So in order to build up the intuition to make a reverb that doesn't sound awful, you kind of have to make a bunch of reverbs. I'm not suggesting there's some kind of magic bullet fix, but I did accidentally, with the help of Geraint, stumble into some techniques that you can use to modify existing reverb structures and rephrase them in a kind of creative way. So hopefully you'll be able to take something from this and be like, I would like to apply this to my reverbs, and something will happen. And as a disclaimer, the said framework for doing that relies heavily on the work of others, but particularly I wanted to mention Geraint Luff's incredible ADC talk, Let's Write a Reverb. Really just an excellent introduction to making reverb an intuitive effect rather than some black magic ritual. So a brief breakdown on what I'm going to be covering. I'm going to start with a brief recap on FDNs, completely switch gears and go into all path chains and then try and combine them with FDNs. Then I'm going to touch on John DeToro and his lawsuits. Finally, I'll be talking about ways that you can modify the structure. So let's kick it off. Algorithmic reverberators can roughly be broken into the following categories. So Schroeder style ones, which like are the first ones people tend to be taught, but kind of sound a little bit like bad. Long chains of all paths and delays. There's a frequency domain approach that Vickers has done. There's wave meshes, which are kind of a black box of non-knowledge for me. Convolution, obviously, and feedback delay networks, which were pioneered by some people. So we are going to do a brief recap on FDNs. They were developed by Gerson because why the cone feedback filter sound like that? But he talks about in his early work parallelizing cone filters through an orthogonal mix matrix to try and improve the echo density and the general like metallicness of the Schroeder reverb. Apparently, Stautner and Puckett then independently discovered conditions for stability for it, as well as coming up with the structure. This guy Jot, I think he's French, I don't know how to pronounce his name, but he then extended that so you can roughly set delay times frequency dependently. My introduction to all this was through CCRMA, the Stanford papers, and DSPrelated.com. The problem being, this is kind of what you're faced with when you're trying to get into it, which is not the most intuitive. So fast forward to me crying to the audio programmer Discord server being like, how do I do this? Obviously Geraint reached out to me with his Let's Write a Reverb ADC talk. Unfortunately, I'm gonna have to paraphrase a lot of said ADC talk. So in said ADC talk, Geraint talks about, a good sounding reverb without months of tuning. You can roughly think about an FDN as a bunch of single channel reverbs kind of mushed together, like the kids in the Pink Floyd's Another Brick in the Wall Part 2 music video. The idea is we have a diffusion stage, which is then fed into a delay feedback stage, which I'm roughly approximating and calling the tank, as it were. So it generally consists of delays, maybe more diffusers, maybe some filters, a gain stage, and a mix matrix. In a lot of the documentation, they will combine the mix and gain stages, but we are going to keep them separate because it makes a lot of the stuff that we're going to be approaching later on a little bit easier to work with. The goal for this is to create the long-lasting part of the reverb. On the other side of the coin, you have diffusers. The goal here is scattered echoes between the channels to try and build up some form of echo density. So in simple terms, start with one thing, want many things, but frequency and volume content the same, which is kind of how you can imagine a 3-year-old might explain a Schroeder all-pass if the 3-year-old has read too much Lovecraft and transcended to higher planes of existence. In the single channel case, our only real option is a Schroeder all-pass filter, unless you want to go to the frequency domain and start twiddling phases, which I would, more power to you if that's your thing, but it gets a bit spicy. But in the multi-channel case, we have access to multi-channel distribution and that kind of thing. So instead of coloring the sound with a Schroeder reverberator or Schroeder all-pass, we can kind of just mix the sound between the channels. So now we've gotten that out of the way, let's have a short breathing exercise and move on to all-pass chains. These are a more kind of traditional structure that you'd expect to see in 80s sort of reverberators, like Lexicon 224s, that kind of thing. Their idea is to build up echo density through all-pass filters and delays, sometimes low-pass filters for frequency-dependent reverberation. You can modulate the delay times and the all-pass times to increase mode density. The idea being you don't want too many ringing frequencies clumped close together or too far apart because it'll be really detectable to the human ear. It can sound great, but there's a lot of all-passes involved. They're really hard to tune for that reason. You have to pick a different delay time for each all-pass filter, basically, and it just gets really annoying to work with. So it's kind of hard to modify, but maybe there's a way we can turn it into an FDN. So this is an example from Spin Semiconductor, just their tutorial on reverb, just a simple all-pass loop structure, which is kind of a bit of a mess at a glance. But the best thing to do here is to try and break it into repeating patterns, try and identify any patterns. And in this case, you can probably see that each independent line of it is just a repeat of the previous one. The coefficients will be different, but the structure remains the same. So let's identify those stages and label them as stages. Cool. Oh, sorry, worth noting, I've skipped over the output taps here because they're annoying. Basically. Anyway, next thing to do is note where the stages connect to. So stage 1 feeds stage 2 feeds stage 3 feeds stage 4, and stage 4 feeds stage 1. Right, let's take a leap of faith and rephrase this as a grid. Let's write the inputs as the columns and the outputs as the rows. And then let's play a really one-sided game of connect 4 with this. So if we start filling in the connections between the stages that we saw in the previous slide, we end up with something like this. I won. So there we have stage 1 feeding stage 2 feeding stage 3, etc., etc. Let's replace the X's with 1s. I spent ages on this. And then let's make it a little bit more austere because we hate color. What we have just done is created a mixed matrix based on the routing between the individual stages from the all-pass loop. Why this is useful is now we can just rephrase the whole thing as an FDN. The point of the mixed matrix is just to distribute routings between the individual stages. Because we split out the gain stage, now all it has to do is say this thing goes to this thing. So if we redraw that as an FDN, we'd end up with something like this, which looks pretty similar to the one that I showed you of Geraint's, with a pretty sparse mixed matrix. But it's easier to reason through, I think. It's open to modifications and it's pretty easily extendable. So from there, that's a simple spin semi example tutorial reverb. I'm going to move on to a DeToro reverb structure. Here's John DeToro now. In 1997, John DeToro released a paper called Effect Design Part 1, Reverberator and Other Filters, which is actually pretty fun to read in terms of like white papers, kind of science papers. It's pretty fun and lighthearted. And he details all the coefficients for this reverb structure. Now, the problem was that it seemed to be an internal document from the Ensoniq ESP2 chip. So they decided they were going to sue him. They were like, no, we can't be having that. And he won somehow. So about this, though, it looks eerily similar to the work of David Griesinger, who was famous for the Lexicon 224 and various Lexicon chips. This is a quote from the Freeverb documentation. I'm not going to read the whole thing, but it's basically saying the DeToro is just kind of a Griesinger reverb, which is kind of the one from the Lexicon 224 with various tweaks. So this is David Griesinger, if anyone was wondering what he looked like. This is the DeToro reverberator. It's kind of supposedly physically inspired by a mechanical tank or a mechanical plate reverb, in that you've got the tank stage having 2 legs, essentially, and they roughly correspond to the sides of the reverb. People call these figure 8 kind of architectures. I'm also, again, going to ignore the taps because they're insufferable, but you can put them in if you want, and it doesn't change the structure too much. So the way to approach this, again, is to try and identify the patterns. But you might notice that some of the stages have different things in them. So the top 2 all-pass filters are inverted, and also you can see that there's an extra low-pass filter thrown in the middle. This is actually fine with an FDN because we can have independent things on different channels. It's not too big of a deal. So let's identify those stages. And there we go. Let's note where they route to again. And finally, let's express that as a matrix. And it turns out that it's the same matrix as the spin semi architecture. So there we go. You know, maybe there's something to that. The FDM representation looks slightly different because not all the channels take input from the input diffusion stage. Obviously, some of the all passes are inverted, and we've added in a couple of low pass filters. Other than that, it's the exact same thing, really. And again, I find it much easier to read. Cool. Hopefully that has given you some intuition on how to approach rephrasing these all-pass chains as FDNs. Next, I'd like to look at modifications. The motivation behind this really is that it's techniques for experimenting with it for someone who might not really know where to start, I guess, and hopefully will generate some new ideas for algorithms from experimenting with these structures. So how can we approach this? First thing we could do is replace the diffuser. Sorry, Geraint. Obviously, we're in the multi-channel case now, so we're not limited to Schroeder all-passes, which is good because Schroeder all-passes tend to have this metallic ring with them when you have high coefficients. The problem is you kind of need high coefficients for the diffusion to get more diffusion. which becomes a tuning problem. So we can just replace that with Geraint's diffuser. It's easier to tune. It's not really metallic. Obviously, it's going to change the sound slightly, but that's kind of what we're going for. So simple change to just drop that in. The next thing we can do is add dimensions to our FDN structure, to our mix matrix. Dimensions is a really spicy word for it. It's basically just adding extra channels, extra feeds through it. So as a general rule, the more channels you have, the quicker you'll be able to build up echo density. Source dude, just trust me. But it ends up being more expensive. So the simplest case I kind of figured was extending this vertically. So instead of a 4x4 mix matrix, we now have an 8x8 mix matrix. Sorry about the impossible to read diagram. I tried my best and my best was not enough. So in this case, the mix matrix just continues along the diagonal for the extra stages, basically just doubling the height of the structure. You can kind of think of it like that. The other way we can approach it is widening. In this case, we have basically just duplicated the entire structure and moved it over one. This is slightly less exciting though, because the two sides are independent temporarily. Like they are just two reverbs running at the same time from the same input. There are things we can do about that, but for now, we can also just replace the mix matrix completely. We can replace it with something like a householder matrix or a Hadamard matrix. These are just designed to get you as much diffusion as you possibly can get, giving you faster echo buildup. The problem with this is that the single channel kind of representation becomes a bit of a mess because we've added a bunch of gain paths into it that are just kind of all over the place. Some of them are negated. So if you want to do that with a Totoro, you may want to mess around with removing some of the all-pass stages. Too much intermixing between channels can actually be a bad thing because it spaces the eigentones closer together, which in practice just kind of results in ringing sounds. That kind of thing. So what if we want to add them in a more controlled manner than that? We could naively just kind of add a question mark line between things. There's a specific feed between the stages. Let's just see what happens. Can we do this? Well, first we have to look at orthogonality. You may remember earlier on, I mentioned Gerson talked about orthogonal mixed matrices. So what is orthogonality? The textbook definition is that it preserves the length of input vectors and preserves the angle between them. In our case, what even are the input vectors, right? The input vector here is just going to be the output from each stage represented as a vector. You can see it there. Magnitude of that vector, so the offset from the origin, kind of represents the total instant energy in the system at that given time. And for this, it really helps to think more in terms of energy than in terms of geometry, because we're dealing with sound, right? Like, it doesn't make a huge amount of sense to imagine a four-dimensional vector and just be like, that's reverb, kind of. So magnitude kind of qualifies the volume in the tank at a given time. So an orthogonal transform doesn't change input vector lengths. We can extend that and say that it doesn't modify the total energy in the system. It just kind of shuffles it around. We don't increase or decrease in volume at any time. We just kind of shuffle stuff around. The reason I kept the mix matrix and the gain stage separate in the earlier example is that that allows us to use orthogonality to kind of categorize our reverb. We could also replace the ones in this with some coefficient for turning stuff down. But if we did that, then we don't really have a nice way of quantifying whether or not it will take off or not. So how do we test that? The formula is a dot a to the t equals I. T here is the transpose of the mixed matrix, A is the mixed matrix, and I is the identity matrix, which is just ones on the diagonal. If this equation evaluates to true with your matrices, then your matrix is orthogonal. So here's an example with the Totoro mixed matrix. I lied. Here is an example with our gain path that we added earlier. So if we notate that as feeds between the stages and test for orthogonality, we'll find that we do not, in fact, end up with an identity matrix. So what do we do about that? Well, we can jump into orthogonal transforms. There are roughly two types of orthogonal transforms. There are reflection matrices, which are kind of boring, as you can see from chat. and rotation matrices. Rotations are really what we're going to look at here. Here are some examples of 2 and 3D rotation matrices. We can extend this to higher dimensions. If you think about it too hard, your nose will start bleeding, so be careful. The other thing we need to look at here is shuffling. You may notice that the Dottore mix matrix is just kind of an identity matrix shifted up a row, right? That's fine to do if our original matrix is orthogonal. But if we apply a rotation matrix to this, we need to line up the diagonals between the two. So here's what that might look like for some rotation matrix. So if we multiply the Dottore mix matrix by this, we end up with all of these things. Effectively, we end up with this matrix. The rest of it is just checking for orthogonality and categorizing it, because we've just embedded sines and cosines. The square of a cosine and a sine will always add to 1, so we end up with an identity matrix. So that's good. We can use this. So that, in the context of our reverb, kind of looks like this, which is kind of weird. Matrix multiplication in general with rotations is kind of unpredictable, but it does work. But it kind of annihilates that figure 8 shape that we had earlier on, right? Like some of the stages are just connected in ridiculous ways, and it doesn't even really make sense to draw this as a figure 8 anymore. But we asked for a game path between stage 1 and stage 3. How can we make that happen? Well, because the rotation matrix is just a rotation matrix, rather than multiplying the mixed matrix by that rotation matrix, we can kind of just shuffle any rotation matrix with the right amount of dimensions so it lines up with the diagonal and drop it in. It's much easier to do it that way than do the multiplying way, and you kind of know what you're going to end up with. It can take a bit of experimentation, but it does work. And finally, here's what you'd end up with if you used that matrix. It is worth noting here that the sine and cosine between, on a single row correspond to almost crossfading between the two stages in a kind of weird, angular, unpredictable way. But yes, this ends up being truer to the original structure doing it this way. One thing I will say is I actually wrote a load of code for this, had audio examples. Doing this is so subtle. Like, it is so difficult to hear much difference. I was like, I'm not spending another 3 days writing code for this just for people to hear a single frequency change. But it does work, and it's quite fun to mess around with. We could use this to, for example, take the 8-wide example earlier and make it slightly more interesting with intermixing between the two disparate stages. So there's my summary. We explored an FDN architecture. We did all this fancy stuff and played a riveting game of noughts and crosses. Thanks for listening. Any questions?
What's your peak then?
Sorry?
Your angle, your peak for the cosine and sines.
It can.
How do you set that?
It can basically be whatever you like. When I was coding examples, I had it on a slider. Now, obviously, if you take the sine of 0 and the cosine of 0, you're going to end up with balance all on one of those paths because it's mixing between the two. So you can experiment with moving that angle, and that effectively balances between the two new gain paths as opposed to the original, if that makes sense.
Yeah, but there's no spatial it's not a spatial representation, so it's not rotation or anything in space or anything.
No, it's more so kind of using a rotation to balance between two things, I would say. Anyone else?
We have a question from the live chat. What is Kalide?
Kalide is many things. Kalide is a company that myself and Ryan, who is next up, have been working for the last 4 years. We make kind of strange plugins and weird, interesting iOS apps, and kind of try and make music production and that kind of approach a little bit more fun, I guess, from a kind of outsider standpoint. Try and make it a bit more arty and a bit more of a kind of let's just see what happens approach, rather than one of those pristine kind of, Pro Q2 kind of approaches, I think.
I thought your architecture was really interesting that we were discussing yesterday about Kalide. Can you tell us a little bit about that?
The architecture?
Yeah, so what do you use actually for these apps?
Right, yeah. So I used Juice mainly for the plugin stuff, and then we one of our projects uses Unity, so we kind of hacked together Juice running as an audio backend for Unity. Me and Ryan pulled a particularly amusing all-nighter and managed to get that work. I think it was like 6 or 7 a.m. we managed to get it working, and then we both just went to bed.
So
Like,
it was a dynamic library.
Yeah.
And then using horrible like C# foreign function interface to call it to like initialize Juice from the Unity project.
yeah, we literally have like a malloc function that we can call from C# to like allocate memory that we then have to, yeah, it's a mess, but it works. So hopefully that kind of answers your question.
Everybody give it.
Thank you.
Fantastic. And yeah, thanks once again. We're live here from near Dublin. I always say Dublin because they've been known that before, Maynooth.
Yeah.
But beautiful out here. And thanks to everybody that's been tuning in online. We have our next speaker that's going to come up and give a talk about the what, how, and why of designing an audio language. And this is Ryan Jeffares. Ryan is a teacher and a freelance and hobbyist software engineer, especially interested in audio education and programming language design. Over to you, Ryan.
Thank you. Let me just get this set up here. And do I have audio? Is it okay? Cool. That should be fine. Cool. Thanks everyone. So this is my talk, the how, what, and why designing an audio language. And I have been interested in this and I want to talk about it. And I felt like I had some percentage of the know-how to talk about it because I'm making an audio language. It looks like this. It's called RAL. It stands for Ryan's Audio Language because I'm really creative. I did the bullet points in the wrong order. And I had some thoughts and I wanted to talk about it. So you can see it's kind of just C sound with curly braces and type annotations, but it works pretty well. And it's been interesting. And I got particularly interested in designing audio languages, or sorry, designing programming language in general. I'm not very good at it yet, but I got really interested in it. And audio languages in particular, I think are really, really interesting. And they hold a special place in my heart, which I will get into. So these are the 3 questions we need to answer. We need to ask, how do you design one at a technical level? What do you actually need to do? What kind of program do you need to write that can be an audio language? What even is an audio programming language as opposed to a general purpose language? What's the difference? And then why do we need audio languages? Why do we need specifically audio languages, these kind of esoteric domain specific languages, as opposed to just general purpose languages using the Juice framework with C++ or something like that, for example. But I'm just going to reorder the bullet points a little bit by defining what an audio language is before I talk about how to even make one. And I should probably justify their existence before I talk about how to make one as well. So really it's the what, why, and how language, but that doesn't roll off the tongue as well. So what is an audio language? Surprisingly, when you Google this, you don't really get any answers. But I decided that it's a domain-specific language, which is a programming language with a higher level of abstraction optimized for a specific use case. You can thank JetBrains for the definition. And in this context, the domain, the specific use case is making audio, processing audio, producing audio, analyzing audio, something like that. So all that domain-specific functionality, I forgot I left those transitions in. All that domain-specific functionality, so sending stuff to the speakers, dealing with audio buffers, dealing with sample rates and everything like that, that is built in. That's taken care of behind the scenes. So when you're writing code, you don't need to write a process block. You don't need to loop over all the channels and the samples in the buffer. You don't need to write your own feedback delay networks from scratch because that stuff is just built in. And realistically, you are using an audio language because you want to write music or you want to analyze music. So instead of having to do all the technical stuff, you can just be creative and you can focus on that thing. these languages usually won't give you like low-level operating system interactions because, again, all the stuff that needs to be done is taken care of behind the scenes. It's taken care of internally. And as well as being textual, so written languages, like most general purpose languages are, in the kind of the world of domain-specific languages, they can also be visual as well, which can make them a lot more accessible for people that aren't necessarily programmers that use general purpose languages all the time. And it will rarely, like a general purpose language like C++ normally would, these languages will rarely compile to a binary file. They'll either be interpreted as bytecode or some other representation, or they will compile to some other kind of media object. So to give some examples that people may have heard of to know what we're dealing with here, we've got C sound, Max MSP, FOST. I was told that was a controversial choice to include. I'm not sure the history. Super Collider, Pure Data, Synthedit. I forgot that what it was. So even within, and I'm very sorry if your favorite audio language is not represented, there's only so much space on the slide. So even within this small contrived list of examples, there's a lot of diversity in terms of the paradigm and how they even work. Max MSP and Pure Data and Synthedit are visual languages, which is unique for programming language because instead of writing words and symbols, you have little nodes and boxes on the screen that you connect together as some sort of graph. FOST is a functional language, so it's typed, it's textual, but it's a functional language. It's a purely functional language, which gets, I believe it gets transpiled over to C++ or even something like WebAssembly first and then compiled to a binary file. Super Collider is a bytecode interpreted language, and it's object-oriented, and it's got all the regular kind of that sort of paradigm. So really, it's a lot like Python. It's almost exactly like Python. So it'll be very familiar to someone who writes that kind of code. And then C sound is, I don't really understand how C sound works. I think that it is written, and then I think that it puts together this like processing chain of opcodes, and it has this messaging system. I haven't been able to really dig through the code that deeply. So why do we need audio languages? Why should we use them as opposed to general purpose languages? So even if you are the kind of person who can do audio programming in a general purpose language like C++ or C or Rust or whatever, sometimes it's simply just overkill to set up a project doing that if you just want to do a quick test or a quick prototype. But more importantly, in my opinion, these high-level domain-specific languages, they make a domain a lot more accessible for people who aren't programmers. Artists and musicians can do amazing things with these domain-specific languages. They do amazing things with Pure Data, with Max, with C sound and stuff, doing installations and stuff. Music producers can make their own plugins using Max and using Synthedit and stuff like that. And then it's also great for learning. It's great for students. I got into programming by using C sound in a module. I didn't do a computer science degree. I did an arts degree. It was in music production, but we had a couple of modules that were using C sound, and that's how I got into programming. And I can guarantee you that if my lecturer, and I had never written a line of code before this, I can guarantee you that if my lecturer sat 19-year-old me down, having never written a line of code before, and said, you're going to go from that to writing audio software in C++ in a semester, I don't think I would have enjoyed it as much as I love C++ now. It's just not as accessible for someone who doesn't write code. So I think it's really important to have these domain-specific languages because it allows people who aren't really into coding to get into coding and have it be a much less painful experience. So how do you make one? How do you even make a language? So you need to pick what kind of implementation you want. And there's a few different ways of doing this. You could make a compiled language, where, as we all probably know, the code is eventually converted into a lot of binary instructions that will be native to the instruction set of the CPU that you're running it on. And these will be contained in an executable file that can just be run. And FOST does this, for example. I know technically FOST is transpiled to something else first, but for all intents and purposes, that's kind of how it's doing. So the advantage to doing this is that you're going to end up with the fastest runtime, the fastest executable at the end of the day, because it will be a native executable. But the disadvantage is that from the implementer's perspective, this is the most difficult way to do things. It's the most complicated. And from the user's perspective, this is also probably the most complicated way to do things, because when you introduce that extra compilation step, if you've got someone who's never even used a command line before and you're trying to get them to use a compiler, it's an extra level of complication. So to alleviate that kind of thing, you could go for an interpreted style as well, where instead of compiling them to a binary instructions, we come up with our own instruction set, our own kind of esoteric instruction set that we can convert the code to, and then we write a program, a virtual machine or whatever, that can run those instructions. And the advantage of this is that it's much easier to do. And Super Collider works this way, for example. But the disadvantage is that it won't be quite as efficient as a compiled executable, because there's that extra level, right? Our compiled executable will be really fast, but the code in our language that we've made up has to go through an extra step before it's actually run. And then, so usually when it comes to general purpose languages, these are the only kind of two ways that you deal with things. But in audio, as I kind of alluded to with Pure Data and Max MSP, we sort of have this third paradigm, or implementation type, that I've decided to call data flow. I don't know if that's a good name, where like in Pure Data and like in Max, we have this visual representation of nodes that are connected together with inputs and outputs. So you have this host executable that can kind of dynamically create this graph representation of our program. And this is quite cool. Now, it's obviously the least portable way to do things, but it is very cool because it means, because this graph is being constructed dynamically, you can change the graph while the thing is running, which makes it really good for live code and stuff like that. So I'm going to center in on interpreted because it's the only way I know how to do it. So this is a little, and I've realized this code is probably going to be tiny on the screen, but on the far left there is an example of my little language that I'm working on. It's an instrument. When you initialize it, it prints hello world to the screen. You give it a MIDI note, you give it an amplitude, and it makes an oscillator and sends those to the speakers. So this code, we can write a program that can read through all this code and convert it into a list of instructions. And then we can write some code. I'm using Rust to write the implementation of it. We can execute those instructions and then compile that program, and it'll all run. And it works. So I will do some examples. Amazingly, it works. How do I, there we go. So we could go, you can play baby's first chord progression. Never mind, no, you can't. Oh no, because okay, never mind. We're not going to do that. You can place bangers. So it works. And if we look at just what that looks like. Now, this language, I will say, is in its very, very early stages. So the ease of use isn't great. It's not very fleshed out yet. But I just set up my instruments, and then the score writing is a little bit tedious. That's something I need to work on. But we've got a combination here of reading samples and doing live synthesis. And it actually works, which I was as amazed as you probably are. So if we just center in on some of the kind of, I don't really have time to go through how to write a language. So for that, I would say read this book if you want to learn how to write a language. Everything I know about making a programming language comes from this book, Crafting Interpreters by Robert Nystrom. It's really, really good. But I can center in on some of the more interesting aspects of designing an audio language in particular. So I'm also realizing this is absolutely not readable on the projector screen, but this is a representation of the grammar of the language. And I can just maybe go to the next slide, which gives a smaller part of it. So this grammar is being represented in the form called EBNF, or extended Bacchus NAR form. And this doesn't really matter, but what's cool about this is we can write, this assumes that we can read the text of the code and split it up into tokens. Tokens being each individual keyword or unique symbol. So, our print keyword open parentheses, close parentheses, semicolon, mathematical operators or whatever. All of these things will be tokens. So we can write what's called a recursive descent parser. This is important because a recursive descent parser can be written in such a way that you can look ahead one token at a time and parse an expression by going through the operators, seeing if the right-hand side of the expression has a higher precedence than the part of the expression you've already parsed, going into that and recursing through the expressions like that. And because we don't need to backtrack at all, I'm just going to go back a slide because that's where my speaker notes were. Because we don't backtrack through the tokens and we only look ahead one token at a time, this parser runs in linear time. So the compilation is really, really fast. So which is why when you run my language or something like Python, for example, it kind of tricks you into thinking that there isn't a compilation step because it basically runs instantly, even though there is a compilation step where the code is being compiled into some kind of bytecode. Because that parser can be so fast, it's really, really quick. But the drawback of that is that there's only a subset of grammars that can actually be parsed that way. There are there's certain grammars that you just cannot parse that way. But the trade-off for having it being really, really quick is I think worth it. You can basically run code instantly. Now, the reason that a language like Python, for example, is not statically typed is because you should be able to call a function or a class that has not been defined yet. And for that reason, you can't really type check. Well, the Python interpreter can't really type check your code while it's doing it because it only does one pass. That's another important aspect of these recursive descent parsers, or one way that you can write a recursive descent parser is you can do it. You can read through the tokens in one pass and emit code as you go. But it limits your ability to do type checking if you have functions and classes, and you should be able to, two functions should be able to call each other, but you can't type check it if it hasn't been defined yet as you read through the tokens. But in an audio language, so there's that. But in an audio language, we're not really in that kind of paradigm where we have functions and classes. We're kind of in our own unique paradigm where, depending on how you do it, if you do it like my language does it, or like C-Sound does it, you've done it in a way where you have instruments that call on built-in components and built-in opcodes, and the instruments don't really need to talk to each other, meaning that as long as you have all the information about all your built-in components, you can do type checking during your compilation. So you can't read this code, but essentially, when we parse an expression in our compiler code, we can return and propagate all the way up what type of the expression was produced. And because of the paradigm that we're in, because we're not calling functions that may or may not be defined yet, we can do that level of type checking, which is really, really, really helpful. And I think makes the language a lot more beginner friendly, because you don't get type errors during runtime. It won't just kind of crap itself if you mess something up. So being able to run type checking, but still having that parser run in linear time really, really quickly is really, really cool. And I thought it was really, really cool how the sort of anti-paradigm of audio languages kind of lended itself to being able to do that. So one other kind of cool little implementation detail that I wanted to share as well is just representing values in the runtime. So even though our language can be statically typed, or my language can be statically typed, when you're storing these values in the runtime of the language, because I'm using Rust, you could use C++ or whatever, which is a strongly typed language, all of the values will need to be represented by the same type. But you can do this in a very cool way with a union. I don't know how readable that code is, but essentially you can have a union containing all the different types that can be contained within your language, and it will be totally safe to kind of dereference that union without doing any additional checks, because we've type checked the language at compile time, which is very, very cool. And that's essentially it. So sort of something that I was thinking about is that a lot of the audio languages that we have are pretty old, really. I'm not really aware of any ones that have been successful anyway, that have been made in recent years. But advancements in writing compilers and writing languages happen all the time, and tastes change as well. And any language that's more than like 15 years old starts to suffer from technical debt and kind of being not changing enough because of it's kind of being held to backwards compatibility. But I think that we have the potential to write really, really good audio languages in the future. And I just thought that it was very interesting because it is an esoteric thing. It is a domain specific thing. You're not really restricted to a known paradigm like object-oriented or procedural or functional or anything. So you can kind of make up your own paradigm with a syntax that lends itself to really helpful compiler end stuff like type checking. So I just thought it was a cool little revelation I had that you can run this kind of type checking very, very quickly in an interpreted language. And I think that I just think that it is something that makes it accessible to people who aren't really coders as well. Anyway, yeah, that's kind of it. Thank you. Any questions?
No questions from the chat.
Okay. I must have answered everything. You're up next. Okay. Oh. Do you want to mute the desk just so I can take this out without deafening everyone?
I'll put that in there. And then.
So, yeah. So I'm nowhere near as good as Josh introducing people, but next up we've got the man, the myth, the legend, Rory Walsh of Cabbage fame to talk to you about P5.C sound. So take it away, Rory.
Okay, thanks for the introduction, and how you all doing? So I don't have any slides, but I have lots of examples. Yay! Yeah, it kind of is a slide. It's just a website actually. So I'll distribute cards later with the web address on it. So the actually I'm just going to put out my phone here so I don't go over because I want to keep this kind of brief. So in the description of this talk, it said that I was going to talk about a CSON library for P5.js. That's a bit of a it's not so accurate because basically all I've done is basically develop a very thin wrapper to an existing CSound web-based package that Stephen Yee and Lovers Sigurdsson published that's a year or two ago now. So this is basically just a very, very thin shim on top of that. So all the credit goes to those guys for developing this. So just a bit about, I've been teaching P5.js for the last couple of years, and I've grown increasingly frustrated with P5 Sound and other JavaScript-based web audio frameworks and stuff like that. So, and as a long-time user of C-Sound, I was anxious to get C-Sound into P5.js in a way that's kind of P5.js-esque, P5G-esque even, you could say. So this is the kind of the fruits of the labor. So basically, yeah. So the first thing is that you don't need to. This package comes as a kind of everything is self-contained into a single JavaScript file. So you don't need to have the CSound library and the P5 CSound thing. It's all kind of compiled down into one thing. You just need to include it in your HTML. So and then the general steps are in your P5.js preload function. You're going to create your instance of CSound. So for some people are familiar with CSound, some people aren't familiar with CSound. The basic premise of CSound is you create an orchestra and then you populate that orchestra with instruments. And then you write a score that triggers those instruments to play. And I say instruments in the loosest possible way. It could be an effect or it could be a synth or anything like that. And a score as well is very, very loose insofar as it's basically an instruction to start something or create an event. So we basically create an instance of CSound. We can pass it different options, like for example, if we wanted to output to the ADS for the digital audio converter, or if we want to say input sound as well, and things like that, we can set our 0 dBFS and number of channels and stuff like that. So we create our CSound instrument. Then at some point, now again, there's lots of different ways of doing this. By the way, once we create that CSound instrument or CSound instance, we basically have access to the underlying C-Sound object, the one that's basically gives us access to anything that you can do with the C-Sound API. So, and I was, you know, I was quite adamant that I wanted to give users, although I provide kind of little utility functions, I was adamant that the users should have access to the all-powerful C-Sound object as part of the C-Sound WebAssembly build. So once we have our C-Sound object, we can evaluate some code. So this is the C-Sound code, right? So people who aren't familiar with C-Sound code might look at this and go, oh. And it also looks worse because I don't have any syntax highlighting on it, except for it's just a JavaScript syntax highlighting. But anyway, so here we've got an envelope. We're going to create an oscillator and we're going to output some sound. That's fine. Okay, so, and then we call C-Sound start audio. So when we call C-Sound start audio, it's going to create an audio context for the web page. One thing to note about this is there was times when I would start the audio and then I would, you know, nothing would happen. I'd hear no sound. It took me a while and some help from Stephen and Dover as well. What was happening was if you don't interact with the web page soon enough after you create the audio context is going to die and it's no longer going to be valid. You're going to be pulling your hair out, throwing things at the computer screen, wondering it worked 2 seconds ago. Why does it not work now? So I've also included a kind of a C-Sound resume audio thing that we can kind of call for each event. The resume audio will just basically, if the audio context is no longer valid, it'll create a new one and we can tap into that. Otherwise, it just ignores it. So building and running locally is not so interesting, but we'll just go to a few examples here. So, right, so we can do stuff like this. Turn that down a little bit. So, and then I just hit reload. Kill that. So we've got this basic instrument, it's just basic sine wave oscillator. What's interesting, so this is, so you've got each one of those balls is basically a simple class, and we instantiate loads of those balls. They bounce around the screen, and when they collide with the outer edges of the screen, we call this trigger sound function, which is defined as this. So we basically just check to see if C-Sound is valid. And here we're going to schedule instrument 1, which is a basic sine wave oscillator, instrument 1 to play for 5 seconds. It's going to have an amplitude of 0.1, and we're going to set the frequency of it. So we can kind of, in this way, we can kind of create some synchronization to the actions that are taking place on the screen. We can also do stuff that's a little bit more, let's say, a little bit more kind of cognizant of what's going on in the environment. So for example, we could, so in this case, we're taking the size of the balls and we're letting that determine the types of sound it's going to create. And we're also making sure there's going to be sound on each bounce. I have to say that this is no way. Yeah, this is in no way. I know Joachim took it from the Andy Fernell stuff anyway. So it's and I just want to say, I want to preempt that this is no way like I'm trying to create an accurate physical representation or model of balls bouncing across the floor. But what's interesting here is we can see we can kind of start to construct some more interesting score statements. So in this case, I'm going to use the mass of the ball to determine the frequency of it. And then as we increase, the number of bounces increases, I have a low pass filter. That's one of Victor's, the Moog ladder filter here. So the sound is getting duller and duller and duller as the balls bounce, and we can kind of hear that here. So again, it's not far from what happens in reality, but it's not that close either. And also I'm shortening the duration of each of those notes as well, because that's really what would happen as well. And also because I don't want to have any kind of saturation. Something else we can do with this is, so working with sound files is obviously something that people try to do. The problem working with sound files and working with any local files with the web-based technology, as you know, is everything is kind of more or less sandbox. So when we want to open up local files, so when we want to read a local file, the first thing we got to do is write it to some kind of virtual storage, which is confusingly referred to as local storage as well, browser local storage, even though it's coming from your local drive. But so those kind of things make it a little bit inaccessible for students because they're thinking, oh, I need to read a file, but why do I have to write a file and all this kind of stuff. Anyway, luckily the C-Sound library comes with, it kind of has an interface to the Node file system. So you can write files. So I wrote it kind of, again, I just put a little kind of wrapper function on that called load asset. Kind of matches the names of the functions that P5JS has as well in terms of load image and load sound and stuff like that. So here we load the local file from our local drive, and then we have access to this file then in the browser memory. And then we can play it by just calling the disk in output like that and outputting it left and right channel. There's just one thing. So in that particular function, you've got the file URL and then you got the file name. And it seems like, why would you have two things, the file URL and the file name? But certain online IDEs, you can't have, just like, especially the P5.js editor. Whenever I just tried to load a file into the browser memory, the virtual memory with the same name as the one that I wanted to use, it just wasn't working. So it's an optional parameter. You don't have to use it. We can also have dynamically loading sound files. So actually, this is not my laptop, so I'm not going to browse here. But so we can so we can load up any sound file and we can interact with it. So one of the things here is that, so this one has a scrubber as well. It moves over and back. You can just imagine, like any audio editor. So another way that you can interact with CSound as well. So the way I've been doing it up to now is just been sending score statements, but we can also do real-time interaction through named software channels. So basically, it's like an auxiliary send and receive. And most of the CSound API kind of driven software, host software, kind of use this a lot for real-time interaction with CSound. And we do this here as well. In terms of when I click on the screen, I'm able to update the sample index within CSound. Audio input, we've got, let's see, does this work? Whoa, I don't know if I have a microphone access. It's like when I speak, this is what people hear.
Actually, might need to change the audio preference.
Oh, yeah. Okay, well, maybe if I hit that. No, not now.
If you go on the preference and see, system preferences and see in the audio.
Yeah, we'll
switch that off.
Okay. Well, I'm not going to do it now because it's not my laptop and because I don't want to mess it up because there's other people using this laptop as well. But if you go to the website, just basically scrolling wave form, it does it in a kind of way that's we have an array and we're just going to pop and push samples to it. I also have this fun game where I can sing into it, and it's kind of like Space Invaders, and you can move the player left and right depending on your pitch of your voice and stuff like that as well. So it's quite easy to have kind of interaction with live input as well. And of course, the nice thing about this, I was talking to some people earlier, some of the web-based web audio frameworks are a bit frustrating because they synchronization and timing is usually gets terrible after some time. But because we're tapping into a native library like CSound, it makes things much simpler. And we don't have to worry about, because CSound is going to give us the master clock that's tied to the sound card, and everything's going to be synchronized. Something else that's nice about the fact that when we compile CSound, when we create a CSound instance, we create an audio context. And from that audio context, we can get the web audio processor node that CSound is part of. And if we have that node, then we can connect into the web audio bigger graph. So it means that we can then kind of use things like the analyzer node to be able to kind of display, say, spectral data and stuff like that. So it's very straightforward and simple to do something like this. So we'll see that we don't need to do an FFT analysis here at all, which is kind of the web audio stuff is going to do it for us. Normally, you'd expect to see some FFT code here in CSound, and then we'll write that to a table, and then we'll somehow try to display the table. But in this case, all we're going to do is we're going to get the audio context. We're going to create our analyzer. We're going to get the node, and then we're going to connect our analyzer and the node together. And then once we have that, we can do something like this. I don't know how easy it is to read, but we're going to create a frequency data array that's going to have all our frequency data. And then down here, we're just going to draw those vertical bars to create our FFT. Of course, that's the traditional way of viewing spectral data. We can also maybe do something a little bit more interesting in this case. So I kind of going to randomly distribute loads of stars around the screen. Each star represents a frequency. And then I've got a very basic synthesizer that's going to play random frequencies. And anytime those frequencies match those of the stars, then you're going to get the stars. They're going to change their density and their size. So it's just basically, yeah, it's kind of a sawtooth synth, but so things like that are really, there's such little code in that. If I click to there's not a whole lot of code for that particular thing, which is kind of nice. W, Command W. Oh, here we go. It's all right. swapping between Mac and PC. So we can do stuff like that. Also, one of the reasons why I was using P5 sound, I was trying to create a sequencer with it at one point. I was pulling my hair out to try to get the synchronization right, but of course with this, it's really quite straightforward. So, so what I'm doing here is I create each of these cells as a class. As I draw them, that's a stop. So that's a stop. Right. So as I click on each of those, obviously anybody's implementing any kind of sequencer, it's a similar kind of thing. We check each vertical column, we trigger the sounds. But in terms of implementation, this is really quite. This is all the C sound code here for that, and that's just the reverb instrument. That's the simple synthesizer. And the thing that's doing all the sequencing is basically this UDO and this instrument here. So this is the kind of the master instrument that's going to kind of move through each of those indices. We've got a kind of channel BPM. We can change so every time I move the slider, it's going to update the BPM, This is kind of neat. It's calls a recursive UDO. So every time it goes in here, it checks every single row, right, of the volume. And if there's a hit, it's going to trigger instrument 2 to play. So it's we can do quite a lot with it, but the implementation is really quite small. And then the last example I wanted to show is this one. So so this it's a generative pad synth, if you like. I don't know what you want to call it. It morphs between 4 different tables. So we've got 4 different separately defined tables. So the tables are like this. So this is anybody familiar with this, and this is Gen 10, and this basically determines the strength of each of the successive harmonics from the harmonic series. So they're just kind of randomly picked harmonics thrown in there just to give each wave table a different sound. And so the idea here is if I run it, so we have so the blue waveform that you see is currently this waveform is currently the rest of the waveforms, but there is a mute over there someplace for the mute, but I can't. Oh, yeah. Okay, I'm just gonna have to reload for a second, stop the audio. So the interesting thing is there's only 4 tables. I'm only morphing between 4 tables, but there's 100 lines across the Z-axis, Y-axis, X-axis, depends whether you use Unity or Unreal, right? So what I do is when the thing runs, right, the first time, as soon as it's initialized, I basically create 100 transitional tables between each of the successive 4 ones. So I kind of move the pointer between each of the 4 tables, and then I write 100 tables. I've got this table manager instrument that's going to write those 100 tables, and then I'm going to draw each of those 100 tables. And then I'm using the index between each of those tables to determine which of the 100 ones is going to be displayed. So, and then that synth, the synth is just a very simple, straightforward synth with a couple of oscillators and a bit of detuning and stuff like that. But it's nice for visualization, kind of looks kind of neat. So I'm using the random indices that I'm using. It's kind of a spin generator. So sometimes it moves through them quickly, and other times it moves through very slowly. So so that's kind of the stuff that you can do with P5C sound. It hasn't appeared on the P5JS list of libraries yet, even though I submitted it at Christmas. But I was told that there's a bit of a backlog, right? So I kind of every so often I open it up, is it there yet? Is it there yet? No, it's not there. So maybe it'll be there in time for next Christmas. But there's links to the repository and stuff online. So just before I go to this, one thing I just might as well show you is how much or how little I have actually done here with this. There should be a link here. Oh, no, check out P5JS, but finally documentation. No, I thought there was a link. Oh, right. Because it's just this really, there's only about 100 lines of code in this whole thing. No, but you'll see it on the GitHub page anyway if you go there. There's a build and there's a release there on the GitHub page. So yeah, if anybody's got any questions, you can just, as we say, just file an issue if you have problems, which means basically it's just someplace for me to ignore all your input. So yeah, any questions? Like. Okay.
All right, we have a question from the live chat. What tools / references would you recommend as an introduction to web audio?
Oh God, I don't know because I don't use it. This is why I did this, you know, this is so I didn't have to get my head into web audio, you know. So I'm not sure, but if it's C-Sound references is a really good C-Sound. There's an online C-Sound manual, the PLOS manual, it's all interactive. That's running C-Sound web as well. So you can go in and you can start editing the code straight away in the tutor or in the manual, which is kind of nice, you know. So, but as for web audio stuff, no, that's what Stephen and whoever, that's why I let them do that stuff, you know, and then we can just pick up all the nice bits and pieces that they leave us, you know. So
Great. And are your GitHub repos for the examples you've shown available for the public? And where can
yeah,
we
yeah,
find
they are, yeah. So actually, well, that's the repo there, right? So, oh yeah, here I can show you the actual. So that's the repo. It's just p5.csound. So it's whatever. How do you work out the?
I got it.
Yeah, you got it. Okay, so but I'll just show you the source. So this is the source. I got it like, okay, guys, that's it. So this, I'm showing this as a testament to the amount of work that Stephen and Lover put into building the actual, you know, the node-based C-Sound package, you know, which
show them show Stephen and Robert's tutorial as well, because they, you know,
the one that they did at the C-Sound conference.
yeah.
Yeah. I'll send it to Josh as well. Yeah, and Josh can put that up online. Yeah.
Yeah, and we'll put all these slides and examples in a package for everybody to have in the video description afterwards. So so everybody asking for slides and for the websites, I'll put all those out after the talk.
Okay, cool.
Thank you very
Thanks.
much for it.
Thanks, guys.
No, go ahead, Sil. I was just gonna say, while we're getting ready for the next speaker, we are going to be having a special on web audio, because somebody was asking specifically about web audio with Hongchan Choi from Google next month, and I will be announcing that date soon. But just wanted to let you know, for anybody that's into web audio, we're going to be having a special on that next month. And I'll have more info on that announcing soon. And I'll pass the mic over to Sil to introduce the next speaker.
Yeah.
Yep. Next up, we got Victor Lazzarini talking about modeling the Korg Prologue VCF. Victor is a professor of music at Maynooth and the author of Spectral Music Design: A Computational Approach. So, take it away.
Hello, everyone. So this talk is quite the fresh work we've done past month or so, and the reason, well, I mean, there's a few reasons for doing this. One is that normally you find that stuff like this, like filters that are modeled, are, you know, models from filters, you know, from the 70s, you know, pushing maybe 80s, but maybe, you know, going all the way to the 60s as well. And this one is a synthesizer that was released only in 2018. And Korg was very nice to provide a service manual for it, so we can actually find out how it works inside. And it turns out that the VCF is slightly different from the VCFs that we find. So it's kind of an original design. And so the product, in fact, appears to be out of production now. So it is now becoming a future classic. So it's good to actually be able to document it, model it, and so on, that maybe, you know, for future generations as well. So I'll start with showing the block diagram of the synthesizer, which is nothing particularly different from other synthesizers. There's a 16 voice and an 8 voice model, and you have like these other voices that get summed up. And there's one thing that's not so, maybe not so good, but it's just something that some people criticize, which is the fact that you have a digital to analog to digital converter here in the middle of the analog path, and then you have a digital to analog converter there. So there's no straight analog path from the voices all the way to the output. And some people may say that, oh, there's some bit of stuff happening here, which is not so good. But I'll leave that out. It's not really our concern. So that's the block diagram. Now we look at the voice architecture, and again, it's a straight subtractive synthesis voice architecture. You have two voltage controlled oscillators, and then you have also a digital oscillator, which is called the multi-engine, and they got all mixed together to the VCF and then to the VCA. There's a few things that are not shown here, which one of them that's important for us is the fact that the multi-engine can go all the way to the VCA, so bypassing the filter, so we can get the output to the multi-engine straight into the output. And also there is what else? There's a few things like there's a drive after the VCF, so it's not part of the VCF, there's a drive before the VCA, so you can actually have some overloading there, but that's actually not something that I'm going to be looking at. I'm going to look at the VCA only, and because we can bypass, we'll be able to use that experimentally, you know, the sound through the VCF and straight out. So now I'm going to lose some friends. So here's the VCF, and you know, apologize for the picture not being very crisp, but and you know, it looks really, you know, wow, a bit sort of hard to sort of take in, you know, at first sight, but we can you know, already find out a few things just by looking at the overall structure. First of all, you have the input here from the mixer, so raw is called, it's an input, and then you have the output there. So that's, you know, you can locate where you start and where you end. Then if you look closely, then you find that there are two centerpieces here, which are common analog circuits called integrators. So they do signal integration here. We'll talk about what integration, what means here in this context, but these are clearly two integrators in a standard type of circuit that you find. And then you find also some means of controlling the gain of the circuit with a voltage, and this is called OTAs, or operational transconductor amplifiers, which are a way of injecting, you know, gain there and change it over time. Then we find that also then there's a feedback here. I mean, you forget you know, there's always a big feedback here, which is normal for every people, but also there is a feedback circuit here that goes here, and that's a fixed gain feedback because there's no only resistors there. So it's not true, but I'll just say that it's fixed again, and then we'll come back, reevaluate that idea later. Then we have the VCF out can go into this bit of circuit here and goes through an amplifier, which is to amplify the feedback there, and then the feedback then goes back from here back into that. Okay, so so we have a feedback part of the circuit there. So there's a fixed gain feedback, and there's a voltage controlled feedback, which is this transistors here are basically controlling the gain of this feedback. It's a bit like the OTAs, but it's actually a differential pair there. Okay, so that circuit is a mess, and we can actually represent it much simpler. You know, so if we go back, all we have in that circuit is signal comes in here, then it gets added to this big sort of feedback from the output, which has no control, so it's just, you know, a normal thing to find in filters. Then you have an amplifier here, the first OTA, then you have the integrator, then you have the feedback that we're just considering here, that there's a voltage control here, so an amplifier there, get some amplifier again, and then another integrator, and you have a sine reversal there, and then you got choke. So that's kind of a flow chart, and from the flow chart, we can progress because otherwise it's a mess. Really, we're not in the business of trying to model each single component. We can have an overview from the top and start working from there. So that's some progress there. So you have basically a gain K that's applied to the OTAs that's controlled by the cutoff CV. So this K here is going to be basically the frequency of the filter is going to be determining that. And then you have what we call damping here, which is this feedback here. And that's as proportional to the inversely proportional to the resonance. So the less damping you have there, the more resonance you have in the filter. I mean, that's actually something that I'm telling you now, but we will understand why actually that's the case later. So now I'm going to lose some more friends by showing some equations here, but it's okay. We have to do that, otherwise we don't understand, we can't progress. So the first thing is very simple. You have this, which is just a simple sum of the output of the filter, which is we call Y, and the input, which we're calling X. So just basically a simple sum, and that's before the amplifier there. And then so that other part there, you can see it's a little bit more, but it's really easy to understand. You have the amplifier K, just multiplier, and then you have an integration. An integrator integrates the signal here. So that signal is a kind of integration of that. That's the integrator, and then the multiply there. Then you have the final bit there, which is a combination of the feedback with the damping and the input, the YB that we just saw integrated again, and that's the amplifier, and then you reverse the polarity. So that's not so difficult. Now, again, you probably won't be friends with me for much longer, but let's try again. So the first thing that we need to say that's really easy to kind of grasp is that there is the integrator that we're using there, and the Laplace transform, which is basically giving you the spectrum of that integrator, is just 1 over S. S, think of it as a frequency. It's kind of it's a complex variable, but we can think of it as frequency, which is exactly what it is. So it's 1 over the frequency. So as the frequency, so it's a low pass filter, actually, this integrator, because it's inversely proportional to the frequency. Now, we can then substitute that in the filter equation to get our transfer function. So first, with the very simple thing, we get so it's just a transfer function of the output, the spectrum of the output, minus 1, which is the input there. The input is just 1. And then the second one, then we can use that expression there. So we have the integrator there, transfer function already, and you have the multiplier, and you can see this is that. Then we can do the next one, which is a little bit more, but not so complicated. So you get that one there, which is there. And so we apply that integrator, and you can see that's the feedback from the output, and then you invert that. Now, this is just a bit of algebra. You can just work out this. You have some unknowns, and then you can figure out the transfer function of the VCF. Now, this might not mean too much for you at this point, but a few things that are important to say. This, we can already say that this is a low-pass filter expression, because you can see the S is all in the denominator here. So that as S increases, this is going to increase, and you have just a scalar here in the numerator. So this is going to be a low-pass, generally low-pass curve. This is a quadratic equation. So it's not that difficult. Huh? You've seen that at school at some point, and so you probably it's not so difficult. This, in fact, is called a biquadratic equation, but only cryptically, because on the top here you don't have, so it should be biquadratic if you had two quadratic equations. But if you had like all the outputs, like the low pass, the band pass, and the low pass and high pass, you end up with a kind of biquadratic equation anyway. Anyway, that's what it is. Now, the interesting thing about that is that when if you know what you're looking there, you see that that's actually something that is not completely unknown. It's something that it's not much of a secret, because there's something called the state variable filter, which you can see it looks a bit like what the VCF, the flow chart, the VCF that we had before, except that things are in different places here. You have this feedback, the dumping here, you have this inversion and so on, but you still have the important things, which are this the gain and the integrator. So it's an integrator-based filter. And the state variable filter is something that's well known since maybe 1967, 68, which then, there was a classic filter on the in the ARP 2500. There was a paper in the AES about that, and it was based on some ideas, some research that was back in the late 60s. So in that, the state variable filter is in various synthesizers, in the Oberheim and so on. And the one thing that's important about the state variable filter is that you have outputs for high pass, band pass, low pass simultaneously. So you put on an input there, and you can tap in parts of the filter and get these three outputs. Now, if we focus on the low pass, then the transfer function for that is that one always, and you say, oh, well, that looks very much like what we had before. So, except for the change in sign here. So we conclude that with this analysis that the Korg Prologue VCF is a low-pass state variable filter with an inverted output polarity. So that's pretty much, so it's a well-known territory. But when you first look at the circuit, you think, oh, what's going on here? I think the clue is that those two integrators that I pointed out, I think that basically gives you kind of a direction to look at and find, oh, that might be the filter. So doing an analysis, you can prove that it is the case. So here's some sounds. We have so this is the sawtooth from the multi-engine, the digital oscillator. So this is just the sawtooth wave. And then you have the filter with no resonance. Then you have the filter with 50% resonance. And the filter 70% resonance, and then cranking up the resonance to 100% to get that. So you would expect, with cranking up the resonance that you have peaking here, and you can see the peaks there. Fine, that's what you expect. The only thing that is unexpected about here, well, you should expect if you think about it, as we'll see later, is that you get all these bumps in the spectrum here, and that's basically not a sign that you have a linear filter here. But because if you have ideal circuits, ideal components, you would have a linear filter. I think that the first thing to do is to try to prove that our equations are correct, to do a linear model then of that. So here's a linear model of let's kind of do the analysis to transform a linear model. So when you try to do a linear model, we can do two basic ways for this particular filter. You have first of all, it's you can do apply the bilinear transformation to the transfer function. So you have a transfer function in the the domain, and you can then translate that to the Z domain. So you have a filter here in a digital filter. So that's you get what's called Z transform or the digital filter, and it's a second order filter. So you can apply a second order section and implement it. The next one is you can use the analog filter structure, replace the integrators by digital integrators, because digital integrators are well known as well. And these have to use also the bilinear transformation. And then you have a set of equations for the digital filter. So you can more or less ignore the transfer function. Kind of, it's good to know the transfer function. And so if you're doing the first one, again, you know, bear with me here, you get this lovely digital transfer function. But that is basically a set of coefficients for a digital filter. So you have, you know, the first feed-forward coefficients are just -1, 2, and 1. So this bit here at the top there, we can think of that. That basically it will give you -1, 2, and -1. You can get then the feedback coefficients, which are basically these guys here over here, given there. So you can see one sample delay, two sample delay, and then you have a scaling thing to apply to everything. So that's good. You can have a filter like that. But the second method is more interesting because it actually allows us to go further beyond the digital, more simply, further beyond the linear model, which is probably your thing. So what you do is this is an integrator. So basically, it's this is the digital integrator here, transfer function, and then when you implement, you can implement that in different topologies. But the topology that we're interested is this one here. So it's basically you have the feed forward part and the feedback part, one sample delay together and get the output. The reason why we want this topology is because we can tap this delay here to get our feedback. And so we don't need to insert one extra sample in the delay, in the feedback delay. So that gives you the set of equations. Now, how do I get this set of equations? I just look at the flow chart. Basically, these are the flow chart. You can see that we get this basically the input. This is one integrator, that's the other integrator, and that's basically mixing the feedback. So now using C-Sound, we have been hearing about C-Sound today. We can just create an implementation of this. So we have the scaling that we talked about before, which we're going to use here. You have applying the gain, which is just that kind of the control that OTA that showed. Here's the integrator, there's two lines. You have the feedback, and adding the signal, you have the integrator again with these two lines. And then you have the low pass output from it. Mind you, you could get the high pass, the IYA is a high pass output, and the IYB is a band pass output. So you can have the three things if you wanted from this equation set of equations. So here's the kind of results. So let's hear that's the original sawtooth. Now I'm going to put that sawtooth through my filter, and we'll see. Well, this looks very much like what we heard before in the Prologue. So it's kind of confirming that we get a filter, and it's like a low pass filter, of course. But this looks like the Prologue, but only around here. This is linear, the linear filter with no other bumps, as you expect. You can see here again, there's no further bumps The other thing is the waveform here is very different as well from what we saw. The other waveform was a kind of a more sort of the same sort of width for the waveform coming down like that. This one is kind of gets wide and then narrow, so it's different. And again, we have a clean thing. Now this should work. So this works like a perfect linear. Probably, the engineers designing the filters in the 1970s, when we were trying to get things like that, what they were striving for was a completely linear filter. The fact that filters came out with non-linearities was kind of a, for them was, we don't want that. But musicians were, but it's kind of too clean. So let's have a look at the non-linear model that we can take from that. So now we're in a good position to go back to the circuit, and so now we're not so maybe in all of it, and we can sort of look at possibilities of non-linear behavior in this circuit. So there's the first ones that are really kind of obvious are these OTAs. Now the OTAs are well known to have a non-linear behavior. If they only kind of linear with voltages around minus plus 10 millivolts. And if they exceed, the voltage is going through them, exceed that, they start to saturate. So it's like a Dunn-H curve. So we can model that nonlinear behavior by translating our multipliers to this Dunn-H, to have this Dunn-H mapping. Now we also add a drive factor G, and the reason for adding this drive factor G is that we don't know really what are the voltages going here, because I'm only looking at the schematic here. I'm not opening my Prologue to put the probe there. So I'm just have to leave some gap, something here, so I can actually play around with the amount of drive, so the amount of non-linearity. Because if that, of course, if that G is very low, then there's not going to be any non-linearity. If we increase that, then there's more non-linearity. So that's not the only one. We have now to look at this feedback path, and we have to split the feedback path into the fixed and variable gain. So here's the fixed feedback path, and then there's the variable gain coming from here. So that those two, then we have to split them into 2 points. So we have that fixed feedback path, and then the kind of variable one, and that replaces the single damping factor that we had in the linear model. Now damping means this is as this signal gets louder, there will be less resonance, because it kind of reduces the amount of kind of a recirculation in the filter. So it kind of reduces the resonance as this thing goes there, because it's going to be the way this sort of addition here, this mixing, it's kind of opposite signs, and they will reduce. Now the resonance actually comes here and from here, and it actually reduces the damping, because you increase that, and they are mixed in opposite polarities. So we have a differential amplifier here to push more signal through, and we can model that again with the Dunn-H, because it's just basically transistors. Now there is a little bit of an assumption here that I'm saying that this is going to have the same behavior as the OTA. So it's as if I'm just replacing that by an OTA, but it works out fine, because you have different types of gain reduction that's happening here and there. So basically, it's more or less the same type of curve, of nonlinear curve that we have. And then the other thing we have to consider is to put like a bit of a Dunn-H mapping at the output of the instrument, because the VCA is also nonlinear, because it's like an amplifier like that. It's also a differential amplifier, and it has some sort of distortion as well, saturation. So we have to put that to kind of reduce the result. So here's the code. Now the code's pretty much the same, except that we're going to have to get the feedback path here, which will split, and then then we have to use the thumb gauge in both multipliers there and here as well in the feedback path, but pretty much the same code with still the the two integrators and so on. So here is to remind you that the original product DCF output. You can see the non-linearities there. And here's talking about the way the waveform is kind of same sort of thickness all the way. And then you have 100% resonance. Again, the waveform is kind of different as well. So here's my model now. So that's the 50% resonance. You can see that has the same bump there, waveform similar. You see the shape waveform. This approximates very well also the 70% resonance, but it's slightly different. There's a few things not quite right, but the sound is not too bad, quite similar. And the full resonance. So it's kind of approximates it with a good degree of likeness. And I think that when you hear it, it's really hard to tell which one is. So the I just select here what the other instrument that I have. So this is more grit in it. Actually, it's not so clean. That kind of does the job, but can we improve it? We're very close, so let's see whether we can improve. So we have a second model, which is not very different, but considers a few other things. So far we have been saying, we have a fixed feedback gain path containing a nonlinear element. There's just we have a feedback path that is fixed, so it's linear thing, but it's not really the truth here. There is this couple of inconvenient diodes there. Now, someone might look at this and say, why, this just conducts this way and that way, so there's cancel each other. There's no reason to worry about that. The thing is that with diodes, they only conduct if a signal level exceeds a certain threshold. So if the signal flowing through here, so coming out of the filter, is below a certain voltage, these guys are closed. So it's like an open circuit. Here, the signal only flows through that and through that. But if they exceed a certain voltage, then this signal starts flowing through there. And so we actually have to consider that this path is not really fixed and has kind of variable gain that is depending on signal levels. In fact, it's kind of an expander type of thing. So we kind of try to model this with piecewise linear. So this is if the path is below a certain value, you have just the usual linear thing. But if it is not, if it's above a certain value, about level there, you actually expand it. This is the values are to do with the resistance we find in the circuit. So it's kind of coming from the analysis. So it kind of has a kink that expands. Instead of saturating, it kind of opens up. And the reason is that when it kind of opens up, it increases the damping and decreases the resonance. So it's a way of squashing the resonance. If there's too much resonance going through, that kind of squashes the resonance. And so we have the transfer function that expander, let's say, here, and we applied that with a table reader here, and basically applied to the filter. The rest is kind of the same. So we just make it nonlinear, make that other path nonlinear as well. So here's again Prologue VCF output. This is which things that we're already seeing, and then that is 100% resonance. And this is the result that we get. Similar to before. This approximates a little bit better if you compare the two graphs. And this again gets closer to the original, although audibly there isn't really that much change. Now we can try to hear that with the maybe there's a little bit in really high resonance. Anyway, it kind of works in kind of a similar way, but it seems to be like more justified to have that, consider that those diodes as well. Okay, so we have some conclusions then that first of all, that the Prologue VCF is a kind of a novel variant on the very well-known state variable filters. I haven't actually seen a restructuring of the state variable in that way that it's in the Prologue. There has been other kind of variants where you actually insert the signal in different places, and has been other ways of actually organizing kind of the network that the state variable is. But this one, the first time I see. But it's interesting also to be able to characterize it as a state variable filter, because people might want to start modifying it. So it's possible to extract other outputs, so you can get the high pass, the band pass, the notch, the out pass, because the filter is discrete. So it's all components there. You have the OT, everything is exposed. It might be possible to do your mods there, and it would be interesting to see if people do that. So you can turn the VCF and put sort of controls that may change the shape of the curve from high pass to band pass to notch or to out pass. This is something that you find in some of the Oberheim synthesizers, and might be interesting here. So you can model the filter linearly in the computer, and it works fine. It sounds good. You can easily derive the other outputs from this. But it's actually, the circuit is fairly nonlinear, as we saw. It produces now this nonlinear output, but we can try to model that by inserting kind of the wave shapers in the kind of locations that we want. So actually, we saw that with these, introducing those wave shapers, we can approximate the original output quite well. And so here's some references. I got the circuit from the Prologue service manual. The diagrams from the start are from the user's manual. There's a couple of chapters from Hutchins you can find on the lecture notes. If you Google, you find those, which are, explain, for instance, the state variable filters, and particularly with chapter 8 here, the voltage controlled state variable filter. So if you're interested in that kind of circuitry, you can look at that. It's a really good one. We did a couple of papers in the last while, which dealt with the state variable filter. First, we did the improving the model, a digital model that was proposed by Hall Chamberlain in his classic book, and we kind of derived a structure that had a number of improvements over his filter. And then we did some nonlinear sort of tweaking of that in the Computer Music Journal paper. And then if you're interested in the bilinear transform, the original paper is from Ken Steiglitz back from 1965. He was the guy who brought that in, although some say that he was one or two people who actually did that, but I like to give the credit to him because he's a very nice guy. So there it is. I mean, hope you enjoyed it and you know, has been useful to you.
Victor, thank you very much. There are a couple questions from the community.
Mhm.
So George asks, and maybe this is beyond the scope of this talk, what would we change if we wanted to make a full component level model of the Prologue VCF?
This in a way is a component model. Well, is a component model in the sense that we start the flowchart from the components. So what we need to consider, maybe if you want to go into component models, you have to look at the integrators and then see the behavior, the nonlinear behavior of the op-amps, which you know, they are not fully linear, so they introduce poles as well in their transfer function. So there is also a little bit of deviation there that's maybe, you know, there's something maybe that you can extract from there. The OTAs are well modeled in this, so there's really not much more to do that. I think the fine tuning is to actually check that all the sort of other things like capacitors and resistors values are you know, doing, you know, what we're doing, and then maybe if we want to do then a component model of it, then we're going to have to just insert all the sort of values in this kind of equations. But maybe I think that at that point is probably you on overkill road very steeply.
Thank you very much. So there are a couple questions from Guillermo. First question goes back to when you said you had a delay shift. So he asks, doesn't this sample delay shift the cutoff frequency? And if it does not, could you explain why your structure does not generate that issue?
Okay, so the problem, if you want to look at the question of the delay, it's this paper here, but I'll just outline what the problem is. If you use, Paul Chamberlain didn't have that, so he had just the integrators, and then at one point he would say, oh, I'm going to get that and feed it back. So you can't feed that back a signal because it's not an analog filter. You have to put a delay there to feed it back. Now, once you do that, the problem is that it works very well up into about 1/3 of the sampling, half the sampling rate, so 1/6 of the sampling rate. And then after that, it goes all pear-shaped. You know, it just basically explodes at the end. So this is a real problem when you put that delay. It just, you know, if you stick in your sampling rate all the way to infinity, then it will work, because then you're putting all the zeros of the filter back into infinity. If you use a very high sampling rate, it will work as well. And so that's actually a good model, because it really models the filter as it is. And that's, you know, that thing is minimized by the high sampling rate. But with the linear, if you don't do that, then you will use the bilinear transform. And the bilinear transform, what it does, it has basically anchors, puts a 0 at the half the sampling rate. So basically it makes the filter, you know, be anchored there. And so that's where it affected the bilinear transform in the integrators. Once you do that, then that also gives you the delay to put back, and everything gets resolved. You get a linear filter that is really sounding very good, like the sort of the ideal model of the filter.
Okay. And Guillermo has another question regarding the diodes. Why not use the known 2 times LS times sine H for the diodes?
Actually, because I haven't tried it. Yeah, actually, it's a good thing. I mean, I just thought the thing with the diodes is that it works like an expander. So basically, I'm just thinking, well, here is linear, and then these bits get, you know, a different gain. So I just kind of create a line that expands and it's a very clunky thing because it's not, should be really nicely bent. So maybe if you use a nonlinear function, like the SynH, you probably get something better. But yeah, I haven't tried it.
Right. By the way, I was going to say, just as a comment,
Yeah.
you've reached the ultimate level when your references are the own papers that you've actually written. So
Well, you
congratulations
could
on
work
that.
on top.
All right. Thank you
Okay,
very
thanks.
much,
Thank
Victor.
you. Thank you.
Right, so go.
All right.
I'll just get your presentation up here.
By the way, I'm gonna just say as a comment, this is really interesting that these talks are next to one another, because in a way they're, it's like two sides of a coin, because this one was about imitating a sound, and then there's the flip side of the coin, which is about the importance of being creative and being able to go outside of your lines. So I'll let Sil.
It's almost like we did it deliberately, right?
Yeah. So we did it deliberately.
Yeah, exactly.
Happy accidents.
Yeah, last talk. Geraint Love on the advantages of hand waving. Well, I'll sit down.
Hi. Wave at me if I'm standing in the wrong place for the camera. Or just wave at me anyway. It's good to be friendly. Hi, I'm Signal Smith, or Geraint sometimes in real life. I head up Signal Smith Audio, a small DSP and algorithm design consultancy over in Cambridge. Yeah, so I've given a couple of technical talks last few years, some at ADC, quite a few on Josh's The Audio Programmer channel, including the Reverb one, which I've, slightly different every time I give it. And I've also got a blog where I write about technical bits and bobs that I find interesting. So I thought I'd try something different. So this is a non-technical talk. It's a bit more philosophical, a bit more personal. And yeah, here's a little summary of what we're going to cover. My story, like, how did I get here? Freeze frame, record scratch, what took me to this point? Not as like an inspirational thing or like anything that's meant to be like relatable or like good tips, but more to kind of explain the perspective of what I then talk about next, which is my main point, which is I think that we can simplify ideas without losing clarity. And in fact, if we can do that, we should. What? Why? And then I give a couple of examples from my personal kind of perspective. How? And then I'll talk about a talk I gave recently, which I'm not holding up as the shining example of this, but I want to kind of talk about the way that I thought about making that talk, and therefore how that fits in with these principles. And then I'm going to have an inspiring call to action, and you'll all leap to your feet. Yeah, great. Okay, so about me. I started learning programming quite young. I think I was like 7 or 8, and my older brother was learning, and I was jealous. So, and I got my dad to teach me as well. And very quickly, I started wanting to do stuff that I didn't have the knowledge for. I wanted to rotate stuff on the screen. I hadn't done trigonometry in school, so my dad was teaching me about that. And I've always loved music, loved piano, and I just loved sound. I think as a lot of you do here as well, I loved sound as this thing that's interactive. And maybe that means instruments, maybe music, maybe it means dealing with it as these signals, this information that you can manipulate or create. When I say I learned programming, this is my dad, who he spent his career as an analog integrated chip designer. So there's a lot of overlap there with sort of the DSP and control theory stuff and circuits, and also because he's designing stuff, that kind of creative thinking. And so it was a huge advantage for me growing up that when I had these questions or this slightly esoteric interest for, like, a 12-year-old, that he was there and had answers. And a lot of the principles of this talk are from the fact that I think my dad was really good
at teaching, and I would like to kind of think about why. So I messed around with Python in my teenage years, and was reading and writing WAV files and having fun and always doing lots of sound stuff, but also other things. At university, I did maths, and I was sponsored and did some summer work by like an audio company. And then when I graduated, for various reasons, I didn't go into that career, and I kind of bounced around a bit. And I always had I had some great times. There were some really good things that I did in that period, but it was a bit lonely in some ways, because I had this big passion for me of sound. And because I was not in a university course, I wasn't at that audio company, there was no one around me who I could just nerd out about with this. And yeah, what actually happened was in February or March 2020, perfect time to quit your job with zero plan. Big shout outs to my partner, Elena, for backing me on this leap into the unknown. And I had this sort of username I'd used a couple of times, which is Signalsmith, all one word, like locksmith or swordsmith. And when I sort of took that leap, I became Signalsmith Audio. One of the last things I did before the lockdowns in March 2020 was I went to another one of these in-person meetups, and it was genuinely one of the best choices of my life. I shook hands with Josh, joined the Discord, and found the great community, which I will actually talk about a bit more later. But again, like, I've got to talk about, the amazing support that my dad, this is me and my dad, that he gave me growing up. And he had this incredible knack for taking complex ideas and not overloading me when I was like 10, but giving me just enough information to give you a really solid and sound understanding. My son's not going to learn that. He's going to do it the proper way, equations first. All right. Yeah, so I'm here to talk about hand waving and how it can be really good and a useful way to teach. So I did some maths tutoring for a while just because I found it quite fun. I like to teach, and I bartered someone for some clothes by teaching them maths. It's not the point. But one of the things that I found interesting is that a lot of people who are struggling with maths didn't have this idea of rules. Like, they were thinking of like recipes or trying to remember things by rote. But fundamentally, a lot of programming and a lot of maths is this idea that like, it isn't an open field of like, you can write anything down on the paper. There are set rules for what you're allowed to do. And you can kind of combine them and build bigger things, but you have these really small building blocks. And maybe rules isn't the right word. Maybe it's like a shape, like a puzzle piece that like has to fit with other things. Or, as a web programmer, there's this thing of like progressive enhancement, right? Which I really kind of, the high level thing has to be kind of working on its own, and then you can add the detail. Or there's another thing, if you look at Google Maps and you're zoomed out, and it just shows you like the big roads, and you zoom in and it gives you all the small roads, and you zoom in, it gives you all the local businesses. It's not telling you anything wrong, but it's adding more detail. But neither of those are like a really good analogy for what I want, because this is hard, right? The thing that I'm trying to advocate here is hand waving can be really good, but it can also be very difficult to do properly. And when I say hand waving, sometimes it's used pejoratively. It means like someone is trying to explain something and there are some details that maybe they don't understand well, or maybe the logic is a bit flawed, and they just go, blah, 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 blah. I don't want to explain this. And I think that sometimes that's the case, but like a lot of the time, explaining wouldn't help, right? The whole point of the hand wave, and for them, the reason they want to do it is because they don't think it helps your understanding. Here is one of my favorite pictures from a cool paper about sort of algorithmic design stuff. What they've done is they've taken a chair and they've done a little simulation of a person sitting on the chair, and they've just taken away all the bits that aren't actually holding any weight. And they've sat the virtual person in the chair and done it again and again and again. And what you have is this skeleton of a chair that is just the pieces that are essential to keep the person aloft. And that is what I mean by hand waving. That is what I would like to advocate we do as people who do understand DSP, as a learning DSP, or I guess any subject. Why do I want people to do this? I think it's really important to keep moving. When I was going through my learning journey, I bounced off C++ first time I tried it. I was 15, had zero patience, and I tried it. I didn't get anywhere. I was frustrated by build systems, and I just carried on doing stuff in Python. And that's fine, right? Like, the point was to keep going, because if you keep moving, you keep interested. Like, all of us who are interested in this DSP world, we're being pulled by something, and you want to keep that momentum going. Maybe there are some situations where you've got, like, you know, a room full of people, they've for a year of teaching, and you can take them on whatever route you want because they are committed up front. But a lot of the time, maybe people are doing this in weekends, maybe they are students, but, you know, you're competing with going out and playing football or whatever else is, you know, in the cinema. And so I do think it is important to keep the passion alive, keep the flame of the interest burning. And then once they're hooked, they will naturally explore the details. You can start with the concepts, and then eventually they will use the equations. So it's also, I think, as a method of teaching, faster and easier for the students. Not for us, but for the person explaining it, it takes more work, because this is hard, right? Doing a proper, when I say a proper hand wave, what I mean is a summary of the ideas, which is simple, but also completely compatible with the more detailed view. And to do that, to make one of those, to communicate, you have to understand the really complicated view so that you know what you're saying is consistent and true. But you've got to find that shortest path, that minimum material to get to that understanding that gives them those puzzle pieces that they can start playing with. So one of my examples is going to be the Fourier transform. What is the Fourier transform? I did promise this is not a technical talk, but, like, is the Fourier transform an equation? Is it a dot product in vector space? Is it a rotation? When I was 18 and thinking of going to university, I was chatting to someone who was, like, trying to figure out if I should do maths, and they were doing maths at university, and they said, ah, yeah, you're interested in that kind of stuff. So, you know, the Fourier transform's like a basis change in an infinite dimensional vector space. And my mind was blown. And I was like, yes, that's it. But that is not the interesting bit I want to talk about. What I want to talk about is when I was in the car on the way home from school, and I was 12. And I said to my dad, how does MP3 encoding work? Because this was the age of Napster, everyone was illegal. Oh, not me. Everyone else was illegally downloading Nirvana. And he paused a bit as he, I guess, recalled everything he taught me so far, and then had this map of knowledge in his head, and then carefully drew a line between where I was and my question. And he said, so you know how harmonics are kind of like sine waves, right? Sounds are often made of sine waves. Well, it turns out that if you, for any sound, if you have the right combination of sine waves and cosine waves, then they all add up to give you the signal that you started with. That's really cool. But if you do that, then we're not very good at the high frequencies, so you can be a bit more approximate about how you store them. Save some bits and bytes on your computer. Now, there are a couple of things slightly wrong with that. It doesn't use a Fourier transform, it uses the modified discrete cosine transform. And I imagined doing this thing over a whole 3.5-minute audio file, and in fact, it's overlapping blocks, but that's not the point. The point is, that was, I think, an excellent hand-wavy explanation of perceptual coding, psychoacoustics, for a 12-year-old in the back, admittedly a slightly niche interest, 12-year-old. But I think that is a great example. And another one, I would argue, is the entire field of computer science. So much of computer science is about trying to make complicated things with neat enough rules that we don't need to care about what's inside them, but that we're not surprised when we look inside. You look at an API, some list of classes and functions, and you can, if you thought about it, maybe guess what's inside. Maybe you look at it and think, I could write that, good thing I don't have to. But you fully understand the rules of how to interact with this object and how you can plug it into other things on a technical, formal level, but not in a way that's code. And I think that there's an analogy there between understanding a lot of these technical ideas about audio without necessarily having to look at the equations. I talked about the Fourier transform. I was messing around with it as a teenager. And I was doing fun things in Python, and at that moment when I was chatting to someone about the infinite dimensional blah, blah, blah. And then at university, I think for the first time, I actually seriously looked at the equation for the Fourier transform. I'd never done it. I'd used it. I knew what it was. I understood it in various ways, and I just never looked at the equation. And I looked at it and thought, oh, that makes sense. Like opening up the program and looking at the implementation. How can we make one of these? If we're trying to explain this to people, and if we want this to be part of the way that we teach audio, what do we need? Firstly, we need a good space for it. There are a lot of, particularly online spaces tend to attract this, where there's this kind of constant one-upmanship that, like, every time you answer something, you've also got to shoulder a little bit and kind of show that you understand the full thing. If you try and answer a question with a minimal piece of simplified route between them and the understanding, then you will often get a bunch of people coming in to like one-up you and be like, aha, you didn't include so-to-so's theorem, you didn't name check this. And I find that very frustrating. And one of the things that I love about the audio programmer and the culture of the group that Josh has created and maintained is that is a space where that type of collaborative, adaptive learning is definitely accepted. So you have to have the right space for it. And we have to find and create the spaces where this type of learning in whatever environment is possible. And this idea of missing detail implies that all detail is necessary, and I don't like it. So you've got to have a space where where everyone understands that not everything has to be said and explained all the time, that everything is part of a learning journey, and that simple and accurate and incomplete is a perfectly valid type of understanding. And this avoids the kind of defensive phrasing that you end up using. I'm not going to name the forums, but the audio program is great. The other thing that I think we have to do is to not lose track of our own journey through learning. So I think it is, that's a hell of a thing to say in the university, who's very kindly hosting us, but like, I think a lot of people who have this very deep understanding of something, and when they're talking to other people, like the language you have to use at that point, because you've had to go so deep, you have the language which is very formalized. You've had to prove you're working every time you write it up and you publish it in paper. And therefore, when you're talking to someone else, the natural language to use is the formal concepts. And hand waving in that point is frowned upon, because, I mean, there's you and I are colleagues. I know you know this stuff. Why would you be using these more approximate hand wavy terms when you could use the common understanding we have? But the problem with that is it's not beginner friendly. I'm not a fan of the word beginner. I'm going to use learner when I can, because it also means kind of the same thing, but also force you to confront what it means if you say, I'm not a learner. But yeah, there are lots of ways that we are exposed to learning resources. You know, there are tutorials and talks and blog posts and papers, which I think just by their form are kind of end up being slightly difficult ways to learn stuff because you're not allowed to hand wave. So I don't know whether this even works for academic papers, but that's one of the reasons that I find them a bit awkward. That, you know, I can read an academic paper and then afterwards I think, I wish there was, you know, title, abstract, TLDR, right? And because I think that's kind of what I'm looking for, and having that at the top and then you fill in the details is exactly how I like to learn. And the other thing I think we should remember is, like, does this have to be hard? Some ideas are genuinely quite complicated, but when we have a piece of understanding that we've achieved through hard work, it is very tempting for us to say, well, that's how you learn, right? I have this deep understanding of something which I hammered together by reading papers until my brain was the right shape. And then you end up thinking or confusing that depth of understanding with the route that you took. And it's, I think, unhelpful in this kind of like, I understand this, I went through this route. Actually, it's a little bit like, I think you could make it easier for people behind you. And part of that is acknowledging that you may have taken a non-optimal route to understanding. And that is difficult to understand. I have the excuse that because I was doing this as a teenager, I have no pride in whether I learned this efficiently or not. I spent years just dicking around and doing things through experimentation. And I'm not holding that up as like a great example of how to learn, but that's my point. That like, I did this the inefficient way, and now I'm in a good position to make someone else's journey a lot shorter than mine. That was that point. There's also this thing about, like, we present whole systems with big fancy names from the paper that they were presented in. And then sometimes you look really close, and as in Sil's excellent talk, love this power. I don't have PowerPoint, so my transitions are much more boring. Keynotes. Yeah. But like, these systems that look complex, and in fact, the talk about the analog circuits as well, the system that looks horrifying on first glance looks a lot nicer and is easier when you abstract things out into building blocks. And when you say, in this case, like an integrator or an all-pass, then you can forget what's inside it and you can take a step back. And I think that that is one of the, like, if you start from the ground up, it doesn't really help, but you can teach from the top down. You can teach and learn these things and explaining how things work with, this is what an all-pass is, look inside it if you're interested. And if you give people enough information about how it works, then they can dig into it on their own. And this is, I think, one of the big things, that it's, if people are learning through these kind of more intuitive, but still technically accurate explanations, then they will naturally fill in the technical details behind them. They will encounter something which makes them want to go and look up the equations, maybe not for the thing they're currently doing, but for the thing they did a year and a half ago. So it is this kind of, you keep them on that journey, you keep them moving through this learning process, and then naturally they will come across situations where that the roots of that understanding thicken on their own. I don't know what this emoji means. I'm going to check my notes because I definitely meant something by this. Oh yeah. Yeah. So people have occasionally accused me of being an expert on stuff. That's what this face means. And there was the talk on reverb, and I didn't think of myself as an expert on reverb. Like, Josh asked me to make a reverb for a client, and I from my perspective, stuck some Lego bricks together and then charged the money. But actually, you know, once you're dealing with things in that kind of modularized way, most things, most good designs end up being those Lego bricks. As for the pitch shifting, now I can talk about my talk. So that's my little dance. I did this talk called 4 Ways to Write a Pitch Shifter. But before that, I wrote a talk called Thinking in Time and Frequency, because this is the talk that I actually gave, and it's just no one noticed. So what I wanted to do was to write a talk about, from trying to give these hand-wavy understandings to get people like, you know, that zoomed out map of the journey from time domain to frequency domain, subband, and then like the full wavelety kind of like perspective. I didn't get as far as the bigness transform, which is one of my next year maybe kind of thoughts. But it didn't have anything to hang on. It was missing that motivation. So I thought, well, what's a good thing that like has a bunch of different approaches that you can use to tell the story, and ends up writing a presentation about pitch shifting instead. One of the things that I was saddest to have to cut out for time, because I did only have 15 minutes, was I think, an explanation of the Fourier transform, which was a little echo of what my dad taught me when I was 12. But one thing I would like to point out, this is a diagram for my method number 2, which is a frequency domain approach based on, you've got your spectrum, chop it up into chunks, and you just move those chunks up and down the spectrum, thereby moving your harmonics while keeping the local stuff phase locked so that it preserves the time features. I was so close to doing this when I was 17, just messing about with FFTs, because I understood, without having looked at all the equations, some stuff about the way that they spread out meant something was happening in time. Phase was important for time somehow. And again, my problem was that I tried to do this on big 15-second chunks, and I should have been doing it on 100 millisecond chunks. I was so close. But this is the point, that like, in some ways, I haven't moved that far. I've spiraled around and taken the long route. And what I want, go away. What I want us to be able to do as a community, as people who want to teach the thing that we're passionate about, is to realize that actually a lot of this stuff is not very far away from the basic understanding. We just need to find much better routes to get there that aren't as intimidating by adding detail that's not needed, that can be added later. So you have to carefully construct these models which are accurate, simple, and incomplete. So this is the point where I talk about what can we do about this? Because like, I spend a lot of my time doing this. Is what it's just how I like to communicate. So I write about like this on my blog. This is how I structure my talks if I possibly can. But here's the thing, this is difficult, right? As I said before, to be able to make these simplified but still technically consistent, low pixel zoomed out versions of these ideas, you have to understand the full thing, right? We, the people with the depth of knowledge, the people who can write the equations, who can prove it, have to be the people who make the best simplified models. And if we don't do that, then, well, what happens? Other people will, someone will make them, right? And then the analogies might be a bit flawed. Like, people don't actually learn by stuffing a bunch of equations in their head. They have to digest them. One of the things I've learned about myself is that I can't hold very complicated ideas in my head. if you give me a complicated idea, I will turn it into simple ideas piece by piece until I have what feels simple to me. And if we don't do that, if we don't help people do that in a way that is consistent with the technical details, then the people who are doing that by themselves, the learners who don't understand all the depth, will be making those efforts, and it will be helpful. Everyone should be trying to do this. But I'm saying that when you're at the top of your craft, you have a duty, I think, to make these simplifying routes for learning. And if we don't, then we make something which is inaccessible. We make something which is, the top flight people in the companies or the groups or the institutions. They talk to themselves, and there is nothing that grounds them to the world around them in that communication way, which makes it very hard to join in. And maybe you disagree with this on like an ideological basis, and you think these things should be accessible. Maybe you think it should be accessible because you need students, or you want new co-workers for your company, and like there's very practical concerns. And maybe you're like me, and you find that you're alone in this. And if you can learn how to communicate in a technically consistent way without burdening the other person with the huge depth down to the gritty details of the knowledge, then you'll have so many more people to talk about this cool thing that we all love, which is audio and DSP and sound. And yeah, that's it. That's my talk. I would say any questions, but I don't think I gave you any solid information. So no challenges, please. No, seriously, is there anything?
We don't seem to have any questions from the chat. I'll give a couple seconds for anybody to ask, but thank you very much. Go ahead.
It's not a question, but I just do something, Victor. You produce so much resources like for learning, so it's funny. I can see parallels with the way you break down problems and the way it was presenting stuff as well. So like I'm interested as well. I can see parallels with also thoughts on building, implementing programming languages and kind of higher level languages and stuff. So do the higher level languages kind of equate to the idea that you have a kind of we'll put this in a box and you can play around with it, and afterwards if you want to open it up and use it. Do you think there's an issue sometimes with some of the softwares that are out there like Max MSD and stuff like that, insofar as the boxes are kind of closed? So once you will kind of say, oh, that's a really interesting thing, but I can't get access to source code and stuff like that. Do you see that as being presenting a roadblock and a potential obstacle then for learners?
Yeah, I agree that there are some great sort of learner-friendly languages environments. I got really into Reaper's JSFX before I took the leap to C++, and that's a wonderful no-build system. It's built into the door kind of thing. But even, then you're still dealing with like memory buffers and stuff. There are some things which are, particularly the visual languages, I find, where once you reach a certain level, you can't break it open. And I think that's one of the things where like this idea of the thing you have to be learning, has to be compatible with the deeper understanding. And, with the Python, for example, I started a lot of Python, and there are big Python libraries that can do STFTs and that kind of thing. But then if you want to do your own, you've got the full power of a programming language there. And so that is more the approach that I favor of learning, is that like toolkits in languages which actually let you go all the way down. So, good documentation, has got to explain not just the API, but the high level concept. Josh and I were talking about this last night about, what does this class do?
Yeah.
That code can't just be self-explanatory, except for someone with enough expertise. If you want it to be accessible to beginners, good documentation is key. Good design of the library is such that you have that natural, you can break it open, re-implement it yourself, and re-implement it yourself until you're writing assembler, right? And so, yeah, that's that.
Yeah, that's cool. Thanks.
Yeah, that brings up a great point that I remember coming from somebody who I work with. Sometimes Pete Goodliff, who's the CTO of InMusic, or the owners of Kai and Audio and several other brands. And for his developers, he says every single class needs to have a description and need to be well commented, because it seems so obvious to the person that's writing it, but to anybody else, it's complete mystery. So no matter how obvious it is, you have to make comments, you have to have documentation. So we have a question from George, who asks, what was the transform that you didn't get to during your talk?
Oh, the Fourier stuff and FFTs.
Yeah.
Like I had a moment in the presentation where I skipped it and said, I'd cut this for time.
Yeah.
And I put a version of it up on like a separate YouTube thing later, but that was the hardest edit I had to do, because my original version of that talk was 2.5 hours. And then I rehearsed it and compressed and edited it for like months until it fit into 50-minute slot. And that was the hardest bit.
Yeah. That's great. Cool. That's all the questions online. Any other questions from the audience here? All right. Well, it's time for a few questions. So, So, pass.
It's me. No, I just wanted to give a massive shout out. Thanks to Ian McCurdy for handling the sound and manning the cameras. You can't see him, but he is here, lurking in the background.
Give a hand for Ian. Woo! Could not have happened without Ian. Thank you very much.
Thank you so much to all of you for coming. Wouldn't have happened without people in the actual room. So, give yourselves either pat on the back or a round of applause or something. Thank you all. And finally, thank you so much, Josh, for having us and having us in your stream and stuff. And Rory, we're going to get that pint later.
Oh, yeah, that way. But thank you very much. A couple things. One, I wanted to definitely make sure we got a group picture before everybody goes. So please don't just run out before we go. We got to get a crew shot after the live stream. Thanks to everybody who tuned in. This is really cool coming out here to Dublin. Thank you to Sil and to Ryan for inviting me out. It's really interesting that this started out with just them basically saying, let's grab a pint, let's talk about audio programming, and that it's grown into this. And I love that it's something that's very intimate. Like I said, it's very grassroots. It goes back to the heart of what we are about at the Audio Programmer, which is making this accessible for everybody. And I really love this wasn't by intention, but that there were a variety of talks that really accentuated that. Everything from Garrett, who was talking about making things accessible at a high level, to talking when it comes to talking about these concepts, to Victor, who is talking about the low level and the actual implementation of these concepts. Everything from writing new languages, writing new ways for people to be creative, to just being able to abstract out concepts like what you've done with your talk. So congratulations, and thank you very much to everybody that came out. It really means a lot, and I'm really proud as a person that was just broke as a college student a couple of years ago to seeing this going around the world. This really means a lot to me. So thank you very much. So we're back online next month. We have some very exciting talks that we're going to be doing online that I think you're going to be very excited about. And the date, I don't have it in front of me. I believe it's August 8th. It'll be the second Tuesday of the month. And like I said, we will be having a web audio special next month with Hongchen Choi from Google. We're going to be talking about advancements in web audio, and we're going to be given an opportunity for the community to ask any questions and talk all about web audio. I think Garrett wants to play a tune. Are you going to play a tune? Yes. So thank you very much. And I'll make sure that we have the slides up. And yeah, make sure we got to get that crew shot. Everybody have a safe morning, afternoon, evening, wherever you may be in the world, and we'll see you soon.